Rocket Science, Part 1, Using Momentum Conservation. How does a rocket at rest, so P for momentum, R for rocket, I for initial, so how does a rocket starting from rest with no momentum reach ever greater speeds, i.e. achieve ever greater momentum? Is momentum conserved for rockets? In order to explain this, we'll use a momentum table. You learned how to use a momentum table in the video lecture. So momentum tables are used the same way we used energy tanks and force diagrams to help organize your thoughts and provide a framework for your analysis. So the first thing you have to decide when setting up a momentum table, decide what system you're analyzing, in this case the rocket, which objects are part of that system. In our case, the rocket is, and the environment is not. So our system starts out P initial, as does our rocket at rest, so no value for the initial momentum of the system or the rocket. Now fuel is also going to be treated as a separate object in our system. So our system will be rocket and fuel. The fuel also starts out with no momentum, as it's part of the rocket sitting on the platform at rest. So our initial momentum of our system, just like the rocket plus the fuel, is nothing. Then once the rocket starts firing and has momentum, we observe, initially it's at rest, and the other observable, P final, momentum at a later point in our analysis. So final doesn't mark the end of the motion. Final just marks the end of the time interval that we're using for our analysis, between some point in time and a later point in time. From rest, so some later point in time when it's moving. Our rocket is moving up, so our momentum vector is up, and our fuel is being shot downwards. Momentum vector is down for the fuel. Now, momentum vector, momentum table, is keeping track of our vectors. We start out with nothing, we end up with something. Therefore, our change in momentum, delta P, which is our impulse added to nothing, to create that something must be the same value. So delta P, the impulse, must be the same value as the final when we start from rest. Now the impulse of the rocket and the fuel are opposite in direction. Rocket goes up, fuel goes down, but they're always going to be equal and opposite impulses. So change in momentum for the rocket is equal to change the momentum for the fuel, opposite in direction, one's up, one's down. And the reason they're always equal and opposite is having equal and opposite impulses within our system means our overall system has no change in momentum. So the impulse or change in momentum of the system is zero, so the momentum before is the same as the momentum after for the system. It's that boxed in zero there, that's the key that tells us our momentum is conserved of our system. Internally, we have equal and opposite impulses from the internal forces of the fuel and the rocket, which keeps the momentum of the system unchanged, zero before and zero after to the system. So momentum is conserved even when an object, such as this rocket, is starting from rest and has motion. So even if it has tremendous motion, yet started from rest, and system with no momentum before and after can still have a tremendous amount of motion, even though the motion of our system, net momentum of our system, is zero. Now, an impulse, change in momentum, as you learned, is a force over time, so you can relate the forces, the impulses, to the forces involved. So a force over the time interval, the force of the rocket over the time interval is changing the momentum. You force something over time to change its motion. The force of the fuel over that same time frame is equal to the change in the momentum of the impulse of the fuel. Equal and opposite impulses in the same delta T means equal and opposite forces. So therefore the force of the rocket and the force of the fuel are equal and opposite. And there's Newton's third law. It's derived from momentum conservation. Now, can we use this similar analysis and show how to describe momentum conservation for a rocket that starts out not at rest, but starts out with some momentum and gains ever greater momentum? So now our rocket is going faster, but our initial momentum of our system is our earlier momentum, which we call the final momentum. So now we switch the final to become the initial. So we have, again, a rocket moving, but now the rocket is added to its momentum to get faster and faster. So how do we use the table momentum conservation to describe this? Well, I start out with something, and I observe that the momentum afterwards is greater, so I must have added momentum in that same direction. So let's say the momentum we start out with is 8 units of momentum. I change momentum by 10, my impulse is 10, so an initial momentum of 8 plus an impulse of 10 gives me a final momentum of 18. Now we know the fuel has its initial momentum is opposite the rocket's momentum for the system to maintain no momentum overall, as we just saw. So the fuel, if the rocket has a momentum of 8, then the fuel has a momentum of -8, so the system overall has no momentum. Equal and opposite impulses, an impulse of 10 to the rocket means an impulse of -10, 10 in the opposite direction in units of momentum, to the fuel. Equal and opposite impulses, 10 plus -10, add down the columns, we end up with 0. The final momentum, 18 to the rocket, means we end up with -18. To the fuel, again, 18 plus -18, adding down the columns, means the system does not change momentum. Total amount of the momentum of the system stays at 0. We add across the rows, and we add down the rows. We add across the rows, and we add down the columns. Let's do an example problem. We start to get more quantitative. Let's say we have continue the same idea. The mass of our rocket is 100,000 kilograms. The mass of fuel is half of that. And let's say the velocity of the fuel being ejected is at a speed of 4 kilometers per second. And for simplification, we'll say that exhaust speed, the fuel ejected, is maintained continuously at 4 kilometers per second. We shoot it out at a constant speed for simplicity. How can we solve for the velocity of the rocket? Well, if the velocity of the rocket starts out at rest, then we can easily solve for that. As we just saw, we set up our momentum table, starting from rest. The system is 0, rocket and fuel. Our impulse creates the momentum we observe after. Equal and opposite impulses. An impulse, like any momentum, is mass times velocity. The final momentum before and after for the rocket and the fuel are equal and opposite. So the mass of the rocket times the velocity of the rocket in the final situation must equal the mass of the fuel times the velocity of the fuel in the final situation. So how do we solve for the velocity of the rocket? Well, we've just given 3 of the 4 variables, the masses and the velocity of the fuel, ejected at a constant rate. Therefore, we can figure out the velocity of the rocket. That's the first thing that you'll solve for. Redo the method and solve for that and turn that into the beginning of the yield. Let's do another example, a little more quantitative. Let's say we have a bottle rocket of only 8 kilograms. And the velocity of that bottle rocket in our final part of analysis is 5. So the momentum, the moving mass, mv, 8 times 5 is 40. So what are these units of momentum? Well, mass times velocity is kilograms times meters per second in standard international units, or SI units. Do we have a name for that unit? Note that unit also is force times time, or newtons times seconds. Do we have a name for the unit of newtons times seconds, or kilograms meters per second? Well, a class long ago didn't like that the momentum doesn't have a named unit, and they decided to name the unit, rather than saying kilometers meters per second, decided to call it chucks, because Chuck Norris can deliver the greatest impulse. So we can set up our table quantitatively. Our bottle rocket has an impulse from rest of 40 chucks, or 40 units of momentum, which gives it 40 units of momentum after, and our fuel that's being ejected downwards has negative 40 units of momentum. Therefore, it's shot down with a momentum of negative 40 chucks afterwards. And again, we add along the rows, 0 plus 40, 0 plus negative 40, and add down, and all the math is consistent. Now, let's do another example, see how to calculate values of momentum to take apart a more difficult problem using the methods you have just been taught. So, first, pause the video, read this more difficult problem, set up the problem, and try to solve it, and then come back and see how we do it. Great. Now that you've done that, let's start analyzing this problem. So we have a rocket here, but we're told this rocket now is in 2 stages. First, why do we break up the rocket into 2 stages? Why do rockets separate into stages? Well, the reason is, the first thing you want a rocket to do is to reach great heights. To reach great heights, the first stage is used to go very high where the atmosphere is thin, so there's less air resistance. Then when you're in the thin atmosphere, you then accelerate to great speed without having to fight much air. Recall that the drag force relates to the square of the speed. So you don't have to waste much fuel going at great speeds lower in the atmosphere where you're fighting much of the air. Thus you can go very fast, start to accelerate, or increase your acceleration in the thin air, and that minimizes the drag. It's more fuel efficient. Then you can dump what we're calling stage 1, which is now empty, whose fuel is just used to get up to a very great height to the thin atmosphere. And once you've dumped that stage, you now have less mass, so your thrust accelerating less mass gives you a greater acceleration, reaching greater speeds in the thin air. We're told that these stages, the first stage is 3 times as heavy or massive as the second stage. So we'll call the second stage m, and the first stage's mass 3 times m. Now, be sure you understand that the second stage, of course, is shooting upwards. Its momentum has been increased from the ejection of the first stage, but the first stage is still going up. It's going up with momentum less than it had before, thanks to giving an impulse to the second stage. It gets an equal and opposite impulse to itself, to the first stage. That equal and opposite impulse doesn't send the first stage backwards, it just slows it down to give a kick to the second stage. But it's still moving up with a considerably great speed, just less so than it had before. We're also told that the speed of that first stage relative to the second stage is 42 meters per second. We'll use that in a bit to help us solve the velocity of the second stage and the first. So how are we going to solve for that speed for the second stage after this separation? Well, we're going to again set up a momentum table. Our 2 objects are stage 1 and stage 2 that are composing our system. Again, stage 1 initially and stage 2 initially are connected. So our initial situation is the rocket before its separated stages. So our system is the rocket moving up with great momentum, and stage 1 and stage 2, of course, are stuck together, moving with the rocket at the same speed, just treating them as separate objects, even though they're connected. And momentum is mass times velocity. Well, stage 2 is the mass of stage 2 times its initial velocity. Stage 1, same initial velocity with 3 times the mass. So hence I've drawn stage 1's initial momentum vector to be bigger than stage 2. We know it's 3 times as big because they're both moving at that same initial speed, 1,000 meters per second as stated in the problem. Which means the system, the rocket, with the combined mass of 4m, moving at that same speed initial of 1,000 meters per second, is now drawn down there. And again, are observable in the final situation. Stage 2 is moving with a greater momentum, so I drew the arrow for stage 2 in that second row to be bigger P final than P initial. And stage 1's arrow is going to move with still going up, but with less momentum, thanks to that kick that it gave to stage 2, an equal and opposite impulse to slow it down, but still on its way up. So we can set up the equation for stage 1 and stage 2. Stage 2 got the impulse, the change of momentum, to increase to m times a new velocity, v final 2. And stage 1 has a new final velocity, less than the initial, or v final 2, of course, has to be greater than the initial. And so the momentum for stage 1 is 3m times its new speed, v final 1, which is less than the initial and less than v2. And again, By adding those impulses, equal and opposite impulses slow down stage 1 on its way up and sped up stage 2 on its way up, which is the purpose of separating the stages, to increase the speed of stage 2 in the high, thin atmosphere. Equal and opposite impulses means the system's momentum did not change, so the same momentum before and after. What is that total momentum? As we saw before, it's 4m times v initial. P total initial and final are the same. So therefore, we can write 4m v initial in the last column for the system's momentum, if it's the same as it was before, which it is, by momentum conservation. So let's start organizing. P initial, 3m v initial, P2, mv initial. We're given the initials, we're not given the masses. We're given the relative relationship between the masses is 3m versus m. And we know the P total. So if we know the P total after and before being 4m v initial, then our P total after 4m v initial is equal to our P initial for stage 1 and our P initial for stage 2, which is the equation you have below. Notice we can cancel those masses, so we don't have to worry about what the actual value of the masses are. And we have a simplified equation where we can relate the speeds together. The initial speed was 1,000, so 4 times v initial becomes 4,000, the value on the right. Let's collect those, get rid of the masses, collect those velocities. And so now we have our first of soon to be 2 equations, which we're going to use to solve for the final speed of stage 2. We have this relationship. We don't know the final speed of stage 2, v final 2. We don't know the final speed of stage 1. So we have 2 unknowns in our one equation. If we had a second equation, we could solve our 2 unknowns. 2 unknowns, 2 equations, it could be solved. Do we have a second equation? We do. We call this relative speed here. What this means, if you are an astronaut in stage 2, it seems to you that you are at rest within your stage 2 rocket, looking at the stage 1 being released, going backwards relative to you at 42 meters per second. That means the velocity of stage 1 after release is 42 meters per second less than the velocity of the rocket of stage 2. To convince yourself of this, if you're in stage 2, you're an astronaut in stage 2, it seems you are at rest, and stage 1 moves back at 42. So we say, in that case, the relative equation, v final 2 becomes 0. You're at rest within the frame of stage 2, and v final 1 simply seems to be moving backwards at 42. But in the frame of observers on the ground, both these stages are moving up. So in the frame of the ground, v2 is just less than v1 by 42. Now, we can solve for the speed of v final 2, this velocity of stage 2. Recall that our change in speed, delta v2, is v final 2 minus v initial. So we could also solve for a change in speed. We know v initial is 1,000. And with our 2 previous equations, we can solve for the speed v2. Therefore, we can solve for the change in speed. Times it by the mass, that's an impulse. So once we solved using our 2 previous equations for our 2 unknowns to solve for the second stage speed after separation, we can then solve for the change in speed, which means we can then solve for the impulse. And equal and opposite impulses means we can solve for the impulse of stage 1, which is the same as the impulse on stage 2. So rearranging and cleaning up, we now know how to solve for the speeds after for both stage 1 and stage 2, and for the change momentum, the impulse. You will solve for all these 3 variables and turn showing me how you did it, setting up these methods and pushing them to completion, and turn that in the L. Only thing you would need would just be a mass to solve for the impulse, and you can use the mass from the previous example we did of 100,000 kilograms for the mass of stage 2. And for the mass of stage 1, we have that relationship to stage 2.